So, hey there everyone, and welcome to Sketch Study presents Boards Back to Back Solid State Part 3. Make sure you have subscribed to our channel. Please like the video for more content. Thank you. Enjoy the video. So, hello there everyone, and welcome to Part 3. Sorry, Part 2 was a bit delayed. This one is very because of the rains and I've got a bad connection. So, we'll be starting with the nose packing in two dimensions. So about right here we have AAA type packing. So in this, the second row is exactly same as the first row. So how does this work? As you can see in this diagram. Okay, so here, so show it to you. Here basically, you have this particle. Okay, then from here, AAA type means that this row is the same as this one. It's the same as this one and it's the same as this one. So in short, on top of this there is one the right on the left, so there is one on every side except for this side where there is a space, there is an open space. Okay. Now next up we have what's the coordination number. The coordination number of this arrangement will be 4. 1, 2, 3, and 4. Okay. Next we have if the center above 4 neighboring spheres are joined, a square is formed. Yeah, consider from this a square is formed. Pretty. So that is why this packing is called square closed packing in 2D. So AAA type it is also known as square closed packing. So AAA type right here is square closed packing. Right. Now next up we have the ABAB type. What is the ABAB? Let's try to visualize this. See, it goes in this row, right? But B it goes in this row, so that means between this space of two particles of A space, there is one particle of B. Okay, you understood that? I'm sure of that. So, this particle. So mean that here there is a space above a space, but here there is a particle above the space. So you simply understand that the coordination would be 6 because there is 1, 2, 3, 4, 5 and 6. So that in short that forms a hexagon. So that is why it is also called as 2D hexagonal close packing, and the coordination number is 6. So here we are done with the 2D close packing. So this is done close packing in 2 dimensions. Now next we have a close packing in 3 dimensions. In close packing, this packing can be obtained by putting 2-dimensional layers one above another. So first of all we will be seeing the AAA type. It is just like the first one, so it is sort of the first one only, where so this one is called as cubic packing because it is sort of the AAA type, but you arrange it in a 3D structure, so that's how it differs from. See, it was like this. When you join lines that I mean the rules, they end up forming the cube extra. See this big cube, and this is another small cube. I used to do this hexagon 1, 2, 3, 5, and 6. 6 are surrounding it. Here, all the triangular voids of the first layer, they are not connected, they are not covered by the spheres of the second layer. First layer, this is the second B, and this is the layer A. The one in light is the second. So, explain this diagram. So, right for this one, can consider layer B. So, just like as you can see it, A and one in black is A and red is B. So that is what this diagram is trying to show here. So first of all, we have in this diagram we have P as a tetrahedral and O as a octahedral. Alright. Okay, so for tetrahedral voids. So whenever a space of second layer, that means HCP, I believe hexagonal packing, that is above the void of the first layer, a tetrahedral void is formed. Okay, simple. So here the second layer and it is above the void of the first layer. These layers are surrounded by 4 spheres which lie at the vertices of a regular tetrahedron. So it is basically this way. So this is the reason it's called tetrahedral void, because this looks like a tetrahedron. Now next we have octahedral voids. This are formed whenever the trigonal voids in the second layer above the trigonal void of the first layer. So this one, and this is just on top of the tetrahedron. We had 3, but there was just one on top which covered it like this. But in this case, we have 3 on top, so there is a void on top of a void. That's pretty simple. Start like, and it's like an octahedron. See it here. That is why it is called a tetrahedral void. Now next up, talking about something here, we have this important, make sure you remember this. For n closed back spheres, there are n octahedral voids and 2 n tetrahedral voids. This is very important. There are always n octahedral and 2 n tetrahedral voids. Okay, so remember, right? Moving on to the next one. Placing the third layer above the second layer. This also comes in 3D. So right here we'll be covering tetrahedral voids. Okay, so tetrahedral voids of second layer may be covered by the spheres of the third layer. See, it's like in this case. So tetrahedral voids of the second layer may be covered by spheres of the third layer. This and this. So something like this hexagonal stacked structure. That's what we call it. Okay. The spheres of the third layer are exactly aligned with those of the first layer. So you can see this. This is exactly aligned with this. So this sort of forms a repetition, and that's the reason this is called the hexagonal closed packed structure. HCP, remember that. Next we have covering octahedral voids. So we just covered tetrahedral voids. Now we'll be covering octahedral voids. So the third layer may be placed above the second layer in a manner such that its spheres cover the octahedral voids. When placed in this manner, the third layer is not aligned with those of either the first or the second layer. So we can see this here. Just like in this case. This is the first layer, this is the second layer, and this is the third layer. But this third layer is unlike the second layer, nor does it match with the first layer. So it's different in every layer. So it is called like ABC structure. ABC, that ABC. Yep, this ABC type pattern is called face-centered cubic or cubic closed packed structure. Right. Pretty simple till now. Next, in HCP for FCC, there is a 12 coordination number. Remember this? Okay. Alright, next. This is making of the formula. How can we make a formula? Okay, we'll be learning this simple. So what is this formula making thing? This basically tells us that, for example, given that A contains X cells here right here, where element Y forms CCP lattice. Element X occupies 2/3 of the octahedral void. Right? It's pretty simple. This the answer this would be 2 3, right? X 2 Y 3. Right. So first of all, you take the numbers of elements in Y in the CCP or FCC. So unit cell would be 4. Yep, obviously. Then you take the number of octahedral voids. So the number of octahedral voids. What was it? Number of octahedral voids is n. And what is n of this one? It is 4. So number of octahedral voids is 4. Okay, next one. You have to take the number of atoms of element X in the unit cell. So that will be X in unit cell. How much is X given? It's given 2 by 3. So multiply 2 by 3 into 4. It's 10 by 3. Okay, here we have. So eventually we get 2 by 3. So we will get the ratio of X and Y. So X we got 8 by 3 and Y we got 4. Okay. So we get data number 4 ratio 8 by 3. This cuts it 2. This comes here, this goes here. So eventually we get x2 y3. Right? This is pretty simple. You can see पता चल जाता है.